Okay. Hello everyone, my name is Maziar Sherbafi. I'm also the scientific...
Louder, please.
Sure. My name is Maziar Sherbafi and I am the scientific coordinator of the Local Assist project. I'm very happy to be here in walking conference. I want to, we already discussed about different aspects of body and some of brain language, and I want to talk a bit more about that and how we try to follow this kind of research in the Local Assist project. So the main aspect, our vision is like this: we want to build some robot that can be used as a human companion. So this is the goal of also Local Assist project and also our research, to make a synergy between human or man and machine or robots or assistive devices movement. So our solution is to build similar mechanics and similar control to humans, and then they might match better. I know that there are some other approaches. I don't say that this is the only, but this is our approach, that if you make these two systems closer to each other, you can better make this synergy that I mentioned before. So we try to decode this brain and body language. We discussed, Andre was discussing before, about the language that we can understand better human movement and so on. So we know that, for example, we have the digital twins. You try to basically make a replication of human decision-making system. And there are also robot twins from Ishiguro's group, and they build a robot which is similar to humans, but what we want to build is assistive twins. Then these twins would work with the same principles as humans. So if you give one signal to both of them, then the reaction would be kind of similar. This is what they call assistive twins. And then this is also with the framework of Local Assist. For doing that, we try to do movement analysis and also ask the clinicians to tell us what are important about the body, and also user evaluation. So since they are discussed before, I jump to the main research approach. So we know that the human body and motor control is too complex, but at the same time it works like a concert, and you see that everything is perfectly matching, and you use different players, muscles, neurons, everything are working in coordination, and probably there are some distributed control, like the nodes for each player, and probably there's also kind of central control, like the signal from the conductor. So this is something that nobody knows how it exactly works, but we are working on this topic. I want to tell our approach about this. So if we consider these two systems, assistive devices or robots and humans, we can say that both of them have this body and brain, and if we can, and also kind of communication language between the body and brain. And if we want to make these two working nicely together, we need to basically understand these different languages, the body and brain language and the interface language. I want to tell you what we are doing at the moment to approach a kind of nice communication language between the body and brain and human and robot. So let's start with the body, and when we look at animals and biological body, we see the actuators, the muscles, and the muscles, you know that it could be very fast, like in this bird, and or very strong, like this elephant, and also it can, for example, be squeezing a small hole. This is a variety of properties that we have in biological actuators. But what we look at, artificial actuators or the engineered actuators, are completely different. So how we can approach them? There are some studies that people try to use muscles like the frog muscle to actuate the real robots, but I don't believe that this is a right way to go, or this is what we can do in the future by putting the real muscle in the robots. We try to edit the book to cover different aspects of novel body-inspired actuators, but what we are doing is a kind of hybrid approach when we try to approach this compliance and also at the same time adjustability of the actuator. When we look at human leg, we have different muscles like the biarticulars, monoarticular, and so on. And there are some robots. This robot is from Kosoda's group in Japan, and they use the pneumatic artificial muscles to replicate human different muscle groups. And in the BioVital project several years ago, we tried to replicate them using SCA, serial elastic actuator, or just springs. But when I was working on this robot, I was feeling that, okay, if you want to go from one movement to another, you need to be always in the sweet spot, the optimal solution, you need to change the springs. So we decided to basically merge these two approach and develop the EPA concept, electric pneumatic actuator, where you can use these, we have motors here, the hip joint, which actuate the knee and hip joints, and we also have pneumatic artificial muscles, the PAMs. So if you need to change the physics of the system and the passive dynamic behavior of the system, you can change the PAM pressure. You can also use them as an energy resource, but we use it mainly now for just changing the dynamic behavior of the system. It's kind of adjustable compliance that, for example, you also use in your robots, daily robot. But it's a very simple, lightweight, and you can easily contact them from one place to another and replicate the behavior of muscles. This is one concept that we are following, and we show that okay, we can improve performance, efficiency, and we can simplify control, improve robustness, and human muscle behavior. With the EPA project, EPA 1 project, we focus on the stand sub-function, which is more vertical sub-function. Now we are switching more towards developing the bipedal version of the same robot. And we also try to basically use this concept in the exosuits. We already developed the exosuit, and Wayne already showed that. And now we are also thinking of replacing the springs with the hands to have this access to changing the stiffness of the actuator. So this is what we have done for body language. I think that this is a way that you can think of future research, how we can improve the body language of the robots to be closer to humans. So our solution so far is EPA, it could be variable impedance actuator and so on. For the second level, we also heard about the template models and the template anchor concept, and you all know about this concept. This is also what we are trying to use. We basically move from simple model like sleep, and with the sleep you don't have access to the balance control. We add the upper body, so when you have the upper body, you need the torque to tune the hip torque and to control the posture. And then we start with a very simple, like a spring, and then we add some feedback and also use the muscle and so on. And finally, we can have the reflex-based control with all the muscles, like the model from Hartmut. And we can, if we understand here, we hope that we can also extend this concept and understand this model better. And in another book that we did, we try to cover these different aspects, and I see several people who basically contributed to this book, like Hartmut, Jonathan, Katia. Yeah, there are several people who helped us to do this book. I think here we try to cover these different aspects. So then all these things can be transferred to assistive device again. If you have this concept of Wade already explained about the FMCA, we'll also talk about it shortly. If you have the gravity action force and tune the stiffness of the muscles or the springs, you can also develop an exosuit and use the same concept here. And we did that. This is our exosuit in action. We use the ground action force from the treadmill. We try to basically tune the stiffness of the virtual biarticular muscle, or biarticular muscle goes from the upper body to the shank, and it actuates basically two joints, the knee and hip joint. So this is the VPP concept you all know, and we already tested that for generating walking in 3D and also running in 3D, and also with perturbation we show that it works, the control concept works. Here you see that there is a perturbation, and it can also recover from perturbation. But this is a kind of control concept, but we believe that it's not like this in our body. We don't really control the VPP position. In CD design, such kind of FMCH, basically, first we put a spring there between the upper body and the leg. With the spring can still generate such kind of intersection point, but it's not robust. Then we use a feedback signal. You can see here, this is a spring. If you just tune the stiffness of this spring using force from the leg, then you will have this equation. It's a very simple equation. You have the same stiffness, but the stiffness is modulated by the ground reaction force. And with that, you can regenerate the VPP. So we saw that it can predict human motor control and the balance control. And here you can see in blue the real signal, and in red the prediction by this simple equation. It's the hip torque. And then basically this is the force modulated compliance concept, and we implemented that on different applications. This is the Lopez exoskeleton, and we apply this controller to control the hip joint and also the hip and knee joint in the Lopez, and we show that you can find some reduction in metabolic costs and also in the energy in the EMG of different muscles. So another application was the prosthesis. Here we used the same concept again of FMC, the force modulated compliance, to tune the ankle stiffness, and basically we generated a similar pattern as we found in human normal walking. So these are at different speeds. We found one specific equation which worked for different speeds, which is not expected. Here we have more than just from the spring. We had the nonlinear spring and also damper. But the beauty of this method was that one equation could work for different speeds. You don't need even to tune the speed. The subject walks, and then based on the ground reaction force, you can tune the ankle torque based on this simple equation. So I shortly talk about this orchestration and concerted concept, and we are working on this concept also in the motor control level. If you use the ground reaction force and give it to different joints, I talked about the hip joint, knee joint, and in the robot we also use it for the knee joint. If we give the same signal to different joints and tune the compliance at different joints with the same signal, then it could behave like the conductor signal, which goes to synchronize the motor control at different levels in the human. And if you have the same concept in the exoskeleton or exosuit, so you can expect a kind of synchronization between the assistive device and the body. Assuming that this is the control strategy in our body, and assuming that we use, I don't say that we use it in exactly the same way, but assume that we use the ground action force to tune these muscles, stiffness or damping or whatever, or activation, and we use it in a kind of comparable manner in our exosuits or exoskeletons. So if something happens, this ground action force will change, and then both systems will work similarly. This is our hypothesis. Yeah? And then you can expect that they match better and they can react to the perturbation and so on. We call it concerted control because we believe that with this signal you can basically use it as a conductor signal and basically synchronize these two different systems. And this is one of the, I cannot show you more because we don't have much time. 2 minutes, okay, good. So then, this is basically the concerted control for this middle level. You can also use other signals as a conductor signal. And for the last thing, it's good that Asaf already explained about this concept, but I also want to address the question from him. The idea here is that if you look at the movement, you will perceive the movement, and if the movement is changing, your perception will also change. If you see a stable movement or unstable movement, your perception will be different. This is the hypothesis here. And we did some simple experiment with the robot, with the simulation, just asked the people to sit in front of the screen, and the robot was just hopping, and then there were two different scenarios. One was hopping higher and another was hopping lower. And we asked them, we basically record the EEG signal and see if you can see some difference between these two signals. And if you can find this relation, then you can use it for evaluation. Yeah? We can use basically the human computer to evaluate the movement. And if it is used for assistance, then you can use it for evaluation of assistance. And we don't know how humans perceive assistance. Everybody uses metabolic cost, but it's not our cost function. It's something that we still need to work on, and we think that using the brain signal could be one way to go. At least it is worth to test that, and you can also use the AI learning algorithm. This is basically the experiment that Sarah already showed, and yeah, here the idea was that if we can really, from the brain signal, we can understand how human is satisfied with this assistance, or you can say preservation, whatever level. And assume that at the end you wear an exo and put a hat on your head and you walk, and then you can auto-tune the parameters, the physical parameters, the control parameters of the exo. If you can basically decode this cost function of human, this is basic. Yeah, that's it. And yeah, we call it brain in the loop optimization, and this is our basically the last level. And yeah, and these studies and also some others are part of the local assist project, and yeah, I would be happy to thank also my colleagues here in this all research. Thank you for it.
Quick announcement, questions until 11 or so. However, the bus will leave at 5 minutes past 11. Sharp. Sharp.
So you're talking about using EEG for like online real-time adaptation. There's so many issues with EEG for mobility and movement. How are you concerned not only about movement artifacts, but also different artifacts like seeing things in your vision, responding to that? That's like, I feel like there's a lot that needs to be done to get there. So
that's completely true, and this is an open question and the new thing. Recently, the people are using this EEG signal also for game, for identifying the human.
if you could wait till you're downstairs to talk, that'd be nice. Thank you.
Yeah, and we are at the beginning of the way, and I think it is worth to test. And there are some methods, for example, for movement artifact, using, for example, dual layer EEG and stuff. But at the moment, I cannot tell you what is the solution. It could be one solution that can basically combine all aspects, but it might be too complex. But using the machine intelligence, it seems that there are some hopes for finding such.
I'm gonna shout later.
Yeah.
Two questions about your stiffness modulation. You increase the stiffness based on ground reaction force, right? Is it not a positive loop? So if you're increasing the stiffness, it would increase also the ground reaction force, and then the stiffness would increase again until you go to infinity.
It is true, but it is basically the concept of positive force feedback that we have also in our reflex control, and it is working because the muscle force will not go to infinity, you know. There would be a saturation.
Positive feedback is only for push-up, isn't it?
It doesn't matter. It can, when you move forward, then the force will drop, and then there will be still positive force feedback. But you can, with that we could generate also a stable hopping. It is a very simple equation. We use the ground action force and just stiffen the knee joint. It works well.
And second unrelated question: did you have issues for implementation for because you need to measure the force, right?
Yeah,
And
that's,
measuring the force usually is not.
yeah, in the robot it's fine because you can put some force sensors in the robot. The experiment that we have done so far is using the instrumented treadmill or the force plate. But now we are also working, we have some options for the insole sensor to integrate that. And it seems that the technology in the force sensing is also growing, and I think we have now collaboration with Kosoda's lab again, and we found some ways to, we didn't implement it at the moment on ground, level walking without training, but I think this is something that we are working on, that I think is good.
Thank you.